between discrete and continuous domain frequency. So we use X continuous domain X capital omega here in the Fourier transform. It's called the radiant frequency, right? But sometimes when we talk in the normal term, let's say we say in hertz. So this one here, this is omega is in radian, right? Just all. So yeah, it's radian. And typically, in real life, when we talk about frequency, we talk about hertz. So in hertz, it is about 2 pi f, right? So when you go around one circle, that's 1 hertz, right? But that one circle is 2 pi. So that's why this is a frequency. So sometimes I tell you that the signal is in 10 hertz, that means 2 pi 10 in this capital omega. Okay? So that is what is shown here. And we already know that when we map from this continuous domain into the Fourier, into the discrete domain, okay, all of these are changes of variable. Then what we have is small omega is equal to this one, the capital omega times t. So if that's why yesterday when you load the ECG signal, it gives you a sequence of number, right? It only gives you a sequence of number. It gives you a sequence of number. The signal will give you a sequence of number. And if you have a sequence of number, the only thing you can say is this statement, it's n. So everyone gives you a sequence of number, and you have to understand what the frequency of that signal. What is needed here is they have also tell you what this interval represents in the continuous domain signal, this t. So either it will give you either t or the sampling frequency, which is equal to 1 over t. You need to know this. That's why yesterday when we experimented with the signal, you have this fs variable, the sampling frequency. And having fs, that will give you this t. And having that t allow you to map what a continuous or analog frequency for discrete frequency.
So yes. That is radian over second.
Yes, sir.
Capital omega radian over
second. Yes. This 1 over second, yes. And this one here, f is 1 over second, which is a hertz. Alright, so that is kind of a technical part, and we will see the Fourier channel. Okay, so I want to show you a couple of figures. We have a lot of nice figure here. You do also have in the lecture notes. So let warm up with some of those figures. Alright. Let me see what another figure we can show here. And now again, emphasize the importance of the sampling theorem. So again, signal in the real life exists in the continuous domain, right? When I talk to you, every second there's something, right? Something coming out. But when I want to store in the computer, I always store a sequence of numbers, right? X number occupies one memory location, right? You cannot store anything, right? So you have to store a sequence of number, and the sequence of number here, that is the discrete domain signal. And then the computer, by just play around one number at a time, right? But it can do very, very fast, and it can do something here. And the beauty of this is in this DSP box, to change something, simply you just change the software, you change some variable, right? And that made it very powerful. So in the early day, you want to do some processing. You take this signal and you want to do some output, and that's called analog signal processing. And inside here, the whole circuit doing the analog signal processing using capacitor, resistor, and so on. Everything is hardwired, really put into the circuit. Now, the ability to bring DSP, as you know, if you take the signal and you can bring it into the computer, then really the power is of imagination. You can do all sorts of very powerful things, right? You know how you play with the digital image processing, right? You capture the image early on, you take a snapshot, and all you can do is just make a printout, right? Very hard to do anything else. But now with the DSP, you put everything on the computer, you can use the Photoshop, you can edit image, you can do many very fantastic things. A lot of the time when the image looks lousy, you can really bring them back, as I show you the picture earlier, right? So the benefit of bringing them to DSP, that's where the power is. Also, for example, if you look, you know it's a cell phone, right? Different countries, they have a very different specification. And it's very hard, for example, if I move from Europe to US, I have to change a completely different cell phone, right? Because it uses different systems. Now, what people now in the mall, it's called the roaming facility. You move to different area. All you have to do is just base station, send you some number, and change this configuration, and boom, you can work on the different country, right? So the flexibility is another power of this. Okay. And then later on here, what we do here is we do digital analog, or discrete domain to the continuous domain. Now the story we have early on about, I have this signal which is really go from minus infinity to plus infinity. So the sampling here go from minus infinity to plus infinity, right? And here. So that is something, again, is unrealistic for a computer. I give you a speak signal, I want you to get the output right away. Now I cannot play you to speak forever and then have everything and then do computation. There's one more element we need to consider now is what happens if I have this signal but I only get a process in the finite interval, right? From n equal to 0 to n minus 1, for example. So that is something we want to see now. And it's moved to the topic of become more and more realistic now. Okay, but is that clear, the motivation? Everybody? Okay. So, what do we have? So, what I said, I have an original signal, and it is, that is xt. And across xt, we have a continuous domain Fourier transform. And we talk about, I can take a signal and turn it into a sequence of numbers running, and that gives me the discrete Fourier transform. I can do the discrete Fourier transform. Discrete time Fourier transform. And this discrete time Fourier transform requires n go from minus infinity to plus infinity, as you see in the formula. Now, computer cannot do that, right? The discrete time Fourier transform is x omega is equal to summation with n go from minus infinity to plus infinity xn e minus j omega n. Maybe I can ask you, imagine I tell you, compute the discrete time Fourier transform using computer. What will you say to me? What problem with that? Any problem with computing it using the computer? Yes. The 2 wrong, right? There's no way I can do this summation. Right? Infinite summation. One problem. Very good. Second guy.
The omega is continuous.
Exactly. Omega is continuous. I cannot solve this, right? On a computer, everything is stored in one memory location, right? And a number is sequence of number. So yes, I cannot solve this. So there's two problems. Very good. So the way to figure out problem, the thing that we practiced yesterday, is we now have to compute the DFT. The DFT now is a way to play with the signal, which is I take from 0 to n minus 1, and I compute the DFT of like n. I compute the DFT of like n.